Section 4.5 in Chapter 4 is called Induced Voltage. And what we're going to do here is we're going to look at a more realistic version of this DC generator, one that has 12 coils, and we'll look at how the voltage is created internally. Again, the real reason we're going through this it's an effort to understand basically how all electrical machines work. And this combination of magnetic fields and rotating coils, it's the basis of everything that we really look at when we're talking about electrical machines. So let's look at some detail on this, and I'll break this section up, I think, into at least two parts to help get through this without, just getting too drugged down in the particulars. So here's a more realistic looking DC generator, and really beyond 12 coils, it gets so complicated in the representation that it's hard to follow. But we're going to look at this, and one thing I want to point out to you, in this chapter, if you have 12 coils, you're going to have 12 slots, and you're going to have 12 commutator bars. They'll always be the same. And hopefully when we get finished with all this, it'll make sense as to why that is. But for the time being, just to know that 12 coils, 12 slots, 12 commutator bars, they'll always match up. You got 12 coils, then they have to, be laid into slots in the armature, of course, so there'll be 12 slots to match the coils, one for each side, and they're overlapped, this lap winding approach. And then each one of those coils has to be connected to the commutator. So, there's 12 commutator bars to match that. Now, let's get back to this basic equation that tells us the factors in the voltage generation. And again, it's flux density times the length of the conductor exposed to the magnetic field times the velocity, how fast it's rotating. And all of those it's proportional to that, and any increases in any of those will increase the voltage, and any decreases will decrease the voltage. So everything's based on that particular equation. Now, what we want to think about is, as we go through this, is we're going to walk through, both a physical construction of a generator, which is what we have here, and what we're looking at, magnetic poles north to south. We think in terms of the magnetic flux lines going from north to south across there. And then the other thing that we want to look at is, here are the coils, and each one of these coils is laid into a slot, around the outside of the armature, and those slots are cut into the armature, which, those coils are laid into, lapped, and you can see also how, like, if we're at coil 1 right here, we're showing both sides of a coil, so if this was coil A, then, one side would be on the top and the other side on the bottom. And then what we're also looking at here are our brushes right here, okay? And we've got one that's designated positive and one that's designated negative. And these are our commutator segments. If we count it all the way through there, right, we would count that we would have 12 of those, which is going to match our number of coils, okay? And then, everything's got this complex connection scheme internally, and all of this comes together so that when we go to the output of these brushes, that's where we connect the load. That's where the voltage is developed. We connect a load to a voltage, then we're going to have current flow through that. Okay, so that's the particular. So this would be the actual physical construction of this generator. And then we can also look at the equivalent schematic diagram of the same generator with the same number of coils. Okay, so let me walk through a couple of things here, and this is on your page 75. He says, you know, here's this coil, and suppose that the voltages induced in the armature occupy the position in 411, and that conductors in slots 1 and 7 are exactly between the poles, okay? So coil 1 and coil 7, they are directly between the poles, and so they are exposed to no magnetic field. So the voltage generated in those coils at that particular time would be 0. On the other hand, if I looked at this position and this position, which would be coil 10 and coil 4, then we're going to see that those two coils lie directly in the maximum position in terms of magnetic flux in exposure. So the voltage in those two coils would actually be at the maximum amount at that time. He points out a couple of other things. He says, due to this thing he calls magnetic symmetry, and really that's just the relationship of the coil to the magnetic field. And really, you know, if you look at this coil here and this coil here, they are in relatively the same position in terms of exposure to magnetic field, and also this one and this one. He says that in the page 76 that the coils in slots 3 and 9 here and here, the voltage induced in those two coils would be the same as the voltages in 5 and 11, and that's due to the relative position, which he calls a magnetic symmetry. Then in figure 411b, which is the schematic here, we show the instantaneous voltages that are in each of the coils. Okay, so if I look at that, you know, and this is, you know, just a given, you know, we don't know exactly how these numbers came to be about, but so let's say they were measured. And what we can see in each of the 12 coils is the instantaneous voltage at that particular period of time. And know that this thing is rotating, you know, very fast, but, you know, we're just taking this instant and we're evaluating it. And what we're seeing here is 0, 7, 18, 20, the maximum, 18, 7. And so 7 and 7, you know, relative position's the same. And then we're going to see a mirror image of that on the other side. And then we also know, and just like we talked about earlier, you know, if there is, you know, if we wanted to put a polarity to these voltages, we could indicate that on the coils across here. And then what that shows us is, you know, if we go from this point here to this point here, then those individual DC voltages would just add. And what we would see is 70 volts here. We'd see the same thing on the other side. We'd see, you know, that same increase from 7 plus 18 plus 20 plus 18 plus 7, which is going to give us 70 volts there. So the voltage that's available between the brushes is simply 70 volts. Okay, and let's see. Also, he says, you know, that, you know, the polarity to this based on this representation, the X brush would be positive and the Y brush would be negative. Okay, let's stop that and then we'll make another video to explain the rest of this section.